from the students. So we will proceed to the chapter that we were studying in the previous class. Okay, let me show you. So in the previous classes, we were dealing about the HVDC converter. So in the previous classes, we have seen the pulse numbers that may according to the your circuits, the pulse numbers differ. That is, you can see that the pulse number for single phase half wave rectifier circuit, the pulse number is 1. Then single phase for full wave, it was 2. Then bridge for it is 2. In 3-phase full wave, it was given as your value 2. Then again we have seen 3-phase full wave, and that means depending upon your circuit that we have taken, then accordingly the pulse number will vary. That vary here, you can say that the pulse number varies from 1, 2, 3, and 6. The choice, so depending upon the choice of converter, we can vary the number of pulses. So these are the some topics that we have studied in the previous classes. These were also we have dealt with this circuit diagram also in the previous classes. All of you must remember these topics. Then accordingly, if E1 was taken as reference, it has the value formula Em sin omega t. Then accordingly, the E2 is the phase difference of 120 degree. Then according to the value of type of Q, whether it is even or odd, the equation can be written as Em cos omega t minus 2 pi by Q. Similarly, the third equation, equivalent equation, EMF can be written in terms of Em cos omega t minus 2 pi Q minus 1 upon Q. Okay, so depending on upon the value of Q, the equation can vary. Accordingly, the P is given as the QRS. Q is the number of groups in your parallel matrix form. A converted taken matrix is well gives in series, and R will give you in parallel condition. So accordingly, the condition has been derived. So for so these are the topics that we have studied in our previous classes. Okay, in the previous class we have also seen this derivation, or you can say this example how it has been solved in the previous classes. Then again in the today's class we will study something called EMF induced. That is this is the EMF induced in the that is, you can say that this is the condition of your line commutated converter. For that we have concluded that three EMF that is given as EA, EB, and EC. The current flowing through EMF EA is given as IA. The current through EB is given as your IB, and current through EC is given as your IC. That is the point of A, B, C, and there is a gauge bridge that is connected with a smoother reactor is connected here, and the current flowing through the DC SPDC link is your ID value. Okay, now from here, this is the circuit diagram of a thyristor. This is the thyristor symbol where there is a three terminal. That is one is your gate, another is your cathode, and that is generated by K, and another is your anode that is generated by A. So these are the some basic things that you have studied in the previous classes. So accordingly, the voltage, it is written the voltage across the bulb before it is fired. That is voltage across the bulb before it is fired. That is for the bulb 3, that is S3. You can say this is the value of the S3 function. As you can say, S3 is given as, here you can say this is the value of the S3. S3 is connected with the EMF, and we will discuss about the E2. If we discuss S3 and S2, that means we are considering the value of EMF B and C. Here you can see that the EMF B and C we have to consider. So for the potential of accumulating EBC, you can write EB minus CC. That is what we have studied in that previous class. That is for the reference point, as you can say EB, EC, and EC is given. So EA is taken as the reference, that is omega 2 plus omega t plus 150 degree with a phase difference of 120 degree displacement. EB is written as in terms of plus 30 degree. Then EC for again minus 90 degree. All these things are reduction in displacement in phase angle at 120 degree, and the maximum EMF value is written in terms of line voltage, line current, that is your under root 2 upon 3 multiply with the line current. So accordingly, so here you can see that we have considered the valve 3 and 2, and valve 2 and 3 are considered with your EMF, that is your EB and EC. So accumulatively, if we find the potential difference between those two terms, EBC, you can write EB for a particular instant t and EC in terms of your C at time t. So accordingly, the value of EB and EC, you should put the value of EB from this equation. You can write under root 2 upon 3 EL sine omega t plus 30 degree. So this is your EBC, that is your under root 2 upon 3 EL sine omega 2 plus 30 degree, and also put the value of EC, that is 120 degree displacement, that is under root 2 upon 3 EL sine omega t minus 90 degree. That will be the value. So accordingly, just take out the common term, that is under root 2 upon 3 EL is the common term. Take out and you will get this equation, sine A plus B minus sine A minus B. If you put those value, then you will get this function. You will get this function, that is 2 cos omega t minus 30 degree sine 60 degree. That means here you can say omega t plus a plus b and a minus b, sine a plus b minus sine a minus b. You will get value equation as your a plus b. Accordingly, the value you should put as the 2 cos A plus B plus C plus D divided by 2. That again you will get your C minus D minus omega t minus 30 degree. Then in the first term it will be minus, then again it will, but that will make this equation, and you will get EBC equal to under root 2 line voltage sine omega t plus 60 degree. As you can say, this cos, you can say cos 1 omega t minus 30 degree. You can say convert this cos in terms of sine in this format, that is cos 90 minus theta, that will give you sine theta. So from there, you if you write cos in terms of 90 degree minus omega t plus 60 degree, you will get your sine theta. So average DC voltage for the range of alpha to 60 degree, that means the delaying angle is your 60 degrees. So if you put the value of VD, average DC voltage, as VD represented as VD 3 upon pi, the range of the alpha, that is firing angle from 0 degree to plus 60 degree, that will the value of alpha to alpha plus 60 degree. Now put the value of EBC. EBC will have the value root 2 EL sine omega t plus 60 degree d omega t. And just take out the 3 upon pi root 2 EL, that is sine omega t plus 60, that will give minus cos omega t plus 60 degree, and the range will alpha to alpha plus 60 degree. So accordingly, the value, just put the value 3 root 2 pi EL cos omega t plus 60 degree minus cos alpha plus 120 degree. That will represent, if you just put the value of different ranges, you will get different values. So accordingly, convert the sine cos a plus b minus cos a minus b, a plus b and a plus d. That will give you this equation, and just solve this trigonometric equation. You will get the VD equal to 3 root 2 pi EL cos alpha. So accordingly, this 3 root 2 EL upon pi, you can write as average DC voltage, that is VD naught. Okay, so this is the average DC voltage. You can say this is the average DC voltage. You can the initial DC voltage multiply with cos alpha. That means if you want to make the value of VD variable, then you should make the value of EL and alpha variable. Okay, let us say EL is constant, then cos alpha will be variable. And for varying the value of cos alpha, you have to vary the value of alpha. That means you have to make the value of firing angle variable, so that you can vary the DC voltage. Now, second component of this second topic of this chapter is your DC voltage harmonics. Second chapter of this second topic of this chapter is DC voltage harmonics. Now it is written that DC voltage waveform contains a ripple. The DC voltage waveform contains a ripple whose fundamental frequency is 6 times the supply frequency, whose fundamental frequency is 6 times the supply frequency, hence contains harmonics of the order h equal to 6. And because of this 6 times, it is written as the harmonics in terms of h equal to 6p. As you already know, we know the value of the DC harmonics as the number of harmonics given as h equal to np. Here the p is your 6 times the supply frequency, so p, put the value of p as 6, and you will get the h equal to 6, and where n is your integer. If you just where n is an integer, now find function of the t in terms of your sinusoidal function. That is, first one was at 0 degree, then proceed firing angle at 60 degree, then 120. Accordingly, you will get the different types of harmonics at the particular instant. So accordingly, the ft is written as a naught divided by 2 plus summation n cos n omega t plus bn sin omega t, just like your Fourier series transformation. You have already seen the Fourier series, how the Fourier series transformation work in your HVDC system. So in here you can write a naught as your 3 root 2 pi el cos alpha. A naught as 3 root 2 pi el upon cos alpha. Here an is given as 1 upon pi upon 3 upon 2. So you will get 6 upon pi. Okay, again the range of this value will be, as you can see in this graph, alpha ranges from alpha to alpha plus 60 degree. You have just put the value of, you have just to put the value of your EBC, that is your root 2 EL sin omega t plus 60 degree. So we have put it the value root 2 EL sin omega t cos omega t d omega t, and the range is given as alpha to alpha plus 60 degree. Now you will get from this equation root 2 EL upon pi by 6. Okay, now from solving this equation you will get this equation, and on some simplification, the value of n is given as Vd naught upon n square minus 1. So, within the bracket n minus 1 cos 1 plus n omega t minus n plus 1 cos 1 minus n omega t, and the range varies from alpha to alpha 60 degree. So accordingly, parallelly, as the an we have found out, similarly the bn can be found out as Vd naught upon n square minus 1, n minus 1 sin 1 plus n omega t plus n minus 1 sin 1 minus n omega t, and the range varies from alpha to alpha plus 60 degree. Okay. So accordingly, the Cn will be under root an square plus bn square upon root. So depending upon the value of different value, you can find the value of a naught. This a naught here, it is written 3 root 2 upon pi el cos alpha. So if you have the value of alpha and el, you will get the value of a naught. Similarly, for finding the value of an, you have to know the value of different parameters that is involved in the equation. Then only you will get the value of n. Similar case occurs for the bn and cn also. So the RMS value of the nth order harmonics of output voltage is given as by this equation. That is RMS value of nth order harmonics of output voltage is given as Cn equal to Vd naught into root 2 divided by n square minus 1. And that equation leads to multiplication with 1 plus n square minus 1 sin square alpha to the power 1 upon 2. Or you can say just under root. You can make this as within the under root. So in general, for the DC harmonics, the equation of the order of the harmonics can be given as h equal to np, where p is the pulse number. As you have seen, if there is a 6 number of pulse, so we have taken there the 6. So the equation was your 6p. Similar, the AC current waveform, we can see that it can be represented. It can be represented as your IS, it is in the y-axis direction, and your 2 pi, that is the angular variation, is given in the x-axis. ID is the HVDC link current that is flowing in the circuit. So RMS value of the current, similarly, that the equation that we have find in the voltage equation is given in the upward direction, but here we are dealing with your RMS value of the current. Now accordingly, if you have the in the previous classes that we have dealt with this RMS value of the current, that is the current flowing the HVDC link. So accordingly, here also you can find 1 upon 2 pi. The range is plus pi 30 degree to your 40 degree. Here you can say 150 degree. That means 30 degree to 150 degree. That is the variation of 120 degree. And the equation is id square d omega t. Here also the equation is alpha plus 7 pi by 6 and alpha plus 11 pi by 6. The value will remain as it is, but here you can see that the id varies from by alpha plus pi by 6 to alpha plus 5 pi by 6 in the upward direction, or for the positive current value, here the equation or the graph is in the negative direction. So the current will vary from alpha plus 7 pi by 6 to alpha plus 11 pi by 6, but in negative direction. That's why here negative value of id is taken. So accordingly, if you solve this equation, you will get this value, that is RMS value equal to your id under root 2 upon 3, that is under root 2 upon 3. That will give you the RMS value of the current. Now the waveform is symmetrical about the x-axis, so you can see that this waveform is symmetrical about x-axis, that is equivalent in the positive x-axis, in the positive y-axis or positive x-axis, symmetrical about x-axis. That will give you the relation in y-axis also, because when you make symmetrical along x-axis, that means some part will be in positive y-axis and some part will be on negative y-axis. Similarly, here you can see that the waveform is symmetrical about x-axis. So a naught will be 0. So a naught will be 0. Accordingly, EL and alpha will be found out. Now accordingly, if you find the value of n, you will get the value 1 upon 2 pi upon 2. So 2 will be cancelled, 1 upon pi will be there. And the range of equation of the current, that is from pi by 6 to 5 pi by 6, 5 pi by 6, and again 7 pi by 6 to 11 pi by 6. Now here it is written id cos omega t d no omega t for the range of pi by 6 to 5 pi by 6. But if you take the range from 7 pi by 6 to 11 pi by 6, as this was symmetrical and this range is in negative y-axis direction, so the current will be taken as the minus id, that is cos omega t d omega t. So accordingly, if you solve this integration formula, you will get your a1 equal to id upon pi within the bracket 2 root 3 sine alpha. That is the final value of your current, that is this is the an value. So here it is written as I, if you put the value of n equal to 1, you will get this equation. Similarly, if you put the value of n equal to 1 for the value of b, you will get this, that is id upon pi under within the bracket minus 2 upon minus 2 root 3 cos alpha. That means there is a variation of a1 with your sin alpha and b1 with your cos alpha. But in case of c1, there is a simple equation that is given as under root a1 square plus b1 square. That will be equivalent to 2 root 3 upon pi into id. As we already know the value of id, what was the value of id? Id and RMS is related with this equation. Id equal to IRMS under root 2 upon 3. That is quite similar to that of this one. Okay, so the RMS value of the fundamental current is given by this equation. As this is the important equation. Should remember all this component, that is IRMS equal 1. That is given by C1 upon root 2. C1 upon root 2 equal to root 2 root 3. As if we split this value, you will get root 2 root 3. So 1 root 2 is taken in the denominator side with the C1. That will give C1 upon root 2. Here you will get root 2 root 3 upon pi. That will make root 6. Root 6 upon pi id. That is the first harmonic RMS value of the fundamental current. Okay. Now the harmonics contained in the waveform of the order, that is given by equation this. This equation is already studied in the previous class. That is how the harmonic order is given. So here you can say the harmonic contained in the waveform of the order is given by h equal to 6n plus minus 1. In general, the h equal to pn plus 1 minus 1. So p is the number of pulse, n is the integer. So accordingly, just put the value of p, you will get the, for the eighth harmonic, the value is given as current is I1 upon h. Let us say this is your h. For the eighth harmonic, you will get 6. So you have to put the value of 6. That will give you the value of harmonic current at that particular presentation. Okay. And next, so this is all about the DC harmonics part. So if you have any problem, then do consult me on the WhatsApp or mail. So the next part is your power factor. Power factor is the basic term that you have already studied in the many places, or in case of starting of the first semester, you are studying what is power factor. But in case of your HVDC system, the power factor should be taken into consideration, because here you can say the DC power must match the AC power, ignoring the losses in the converter. That is the ideal case. Now, for the ideal case, the DC power must be equal to AC power. So for the DC power, there will be no involvement of power factor. So it is written as VD into ID. But for the power factor, AC power, there will be some involvement of power factor. That is, it is represented by cos phi. So the line power that is given as for the this is voltage line. line voltage, this is the line current, this is the cos phi, that is power factor between line current and line voltage, and this is the three phase AC power given. So here just put the value of VD, you will get 3 root 2 upon pi EL cos alpha, and ID is as it is, remain as it is. Similarly, root 3 EL, I put the value of I1, that is root 6 upon pi ID cos phi. So cancel out many terms, cancel, there will be many terms will be cancelled out in the LHS and RHS. So accordingly, if you find the value, you will get cos alpha equal to cos phi. That is the AC power factor is equivalent to the DC power, that is your cos phi, that is your cos alpha. Okay, so here you can say if the alpha varies, the cos phi will vary. If alpha is increasing, the cos phi will decrease. As you can say, for the particular value of cos alpha, if you increase the value of alpha from 0 degree to, let us say, 90 degrees, so for the minimum value of alpha, the cos alpha will be higher. A similar case, if the alpha will increase, the total cos alpha will decrease. Similarly, for the increment of cos alpha, you can say that cos phi will decrease accordingly. So the next part, that is according to your this equation, that is AC power factor is equal to DC power factor. Next part is analysis of 6 pulse inverter with overlap. 6 pulse inverter with overlap. So this was the simple diagram that we have already dealt in the previous classes. So also here also we will discuss there the discuss in 3 mode. First mode, when 2 and 3 valve will be conducting, that is for your conduction angle, that is will be less than 60 degree. Then second mode, in the case, then only 3 valve will conduct, third valve will be conducting, that is when mu equal to 60 degree. Sorry. Module 3, and the mode 3, that will when valve 3 and 4 are conducting. In that case, the mu will be greater than 60 degree. So these are the 3 modes that we have to study. Okay, here you can say this is the circuit diagram to explain the mode 1, where the analysis of valve 2 and 3 is taken into consideration. So here also we have seen this is the EMF, that is first EMF, that is represented for the EA. The connecting inductor is given as your LC, that is smoothing. This is the smoother reactor. Okay, the inductance connected with EA is named as LC. Similarly, EB is given as LC, and the current flowing through this EA is given as I1. The current flowing through this EB is given as I3, and the current flowing through this EC is given as I2. Here are the Thyristor connectors. So we are considering about only the valve 3 and 2 and 3 connected. So here these both are connected with the point B and C. That means made short circuit. Here the smoother conductor. And here you can see the DC current that is flowing. Now you can say this is the theoretical explanation here. Here the theoretical explanation given according to this circuit diagram. So let us concentrate on the theoretical concept, that is what is written. So because of the source and load inductive, the load current will not fall to zero immediately. That means load current will not fall to zero immediately. There will be transient period of output current between the incoming thyristor and outgoing thyristor. So that period is called overlapping. Okay, that is the conduction time is also called as a overlap angle. Here you can say there will be a transition period of output current between the incoming thyristor and the outgoing thyristor. So the period is called overlapping. That means the time when one thyristor is closing, another is opening. In that condition, that angle is named as a overlap angle. Now you can say thus when 1 and 2 valves are conducting. Here you can say valve 1, 3 and 2 are considered. So for first case we have considered when valve and valve 2 are conducting. Thus when 1 and 2 valves are conducting, valve 1 turn off, that is outgoing thyristor, and valve 3 is switched on. Okay, out of these two, 1 and 3, valve 1 is off and valve 3 is on. In that case, when valve 1 turns off and valve 3 is switched on, since the current through them gradually rises and decays respectively, the current through this is given by this equation. For the ABCD, this equation will be given, that is EB minus EA, the inductance LC, the rate of change of the current, that is the current flowing through your third path, that is your I2. You can say the valve 3, you can say here the I3 is given minus di1. So accordingly, the LHS in the above equation is called commutating EMF. This is called your commutating EMF, and this commutating EMF that we have discussed in the previous section also, that is given as EBT minus EAT. Just put the value of EB and EA, you will get this equation, and by solving this equation, you will get this, that is EBC. You will get root 2 EL cos omega t plus 60 degree. When you want to convert this cos into sine, you will get omega t plus 60 degree. That is the condition. So here you can say we are not converting that cos in terms of or you can say just convert cos omega t plus 90 degree, you will get sine omega t. So here EB minus CA, you are getting plus root 2 EL sine omega t. That is the equation of 2. Now from equivalent circuit, the I1 will be taken as I1 equal to ID minus I3. So just put the value of equation 2 and 3 in equation 1. Here you will get, here you are getting EB minus EA, and you are getting I1. So just put the value of EB minus EA equation in this equation, put the value of I1 here. From here, that is I1 equal to ID minus I3, or you can say I3 equal to ID minus 1. Just put those value and you will get this equation as ID equal to IS cos alpha minus cos alpha plus mu. Okay, there is an involvement of mu in this equation that will change the value of HVDC, that can change the value of this HVDC link current. Now here the IS value is given as root 2 EL 2 upon 2 LC omega. Okay, here if you want to find the value of this IS current, then you will get root 2 EL, that is line current, divided by 2 inductance that is connected across the corresponding EMF, and this is the omega. Omega is the 2 pi f. एक minute. So we were discussing about this value IS. That is IS, you can find this equation as root 2 EL upon 2 omega LC. Just put this value, put the appropriate value, you will get the value of IS. And just by putting the value of IS, you can find the value of ID. Now let's talk about the average DC voltage. Now you can see that the average DC voltage, that's DC voltage without overlap, is given by this equation VD equal to V naught cos alpha. Now what will happen if we do the overlapping? Here you can say this is the your zoom in part for the particular waveform. Here you can say this is the equation for EA, this is the equation of EA plus EB. here you can say this is the condition of EA plus CB divided by 2, and this equation is for the graph A. So from here you will get the VD1, that is the 1 upon pi by 3, that lies from alpha to alpha plus mu, and equation will be EV minus EA plus EB divided by 2 d omega t. Now accordingly, if you solve this equation, you will get 3 root 2 upon 2 pi EL cos alpha minus cos omega plus cos alpha plus mu. Now the net average voltage due to overlap, that is voltage without overlap minus average voltage at overlap, you can minus, just subtract the value and put the value, you will get this equation Vd equal to V naught upon 2 cos alpha plus mu. Oh, that is the equation fifth. And when we talk about the equation fourth one, you will just put the value, substitute into 4 in equation 5. From there you will get Vd equal to Vd naught upon 2 cos alpha plus cos alpha minus Id upon Is. Okay. Accordingly, if you solve this equation, you will get this sixth equation, that is given as Vd equal to V naught cos alpha minus Id upon 2Is. Now, where the value of Rc is given, accordingly, the value, when you solve this equation, you will get Vd equal to Vd naught cos alpha minus Rd into Id. Rc, you can relate this equation, you will get Rc equal to Vd naught upon Is, Vd naught upon 2s. Okay, so accordingly, it is written here, this is Rc equal to 3 omega Lc divided by P, or you can say Vd naught upon 2Is. So here the inverter operation, or you call the converter station, it is written Vd naught cos alpha, that is the variable function. Here the resistance is given as the converter resistance, and the voltage developed across the open circuit is given as Vd, and the current flowing through this circuit is given as Id. Now the waveform shows the output voltage and the valve voltage. So the valve voltage, this is the topic that we will discuss in our next class. So all of you must go through this class notes, or the class that I have taught you today. Okay, if there is any problem, do consult me. Okay, thank you for today's class. Thank you.